So we are looking at exercise 4B on page 99 of the workbook. This is one last example of determining whether a series converges or diverges. Those are the instructions that go with this question. Okay, and again, we've got this whole list of series convergence tests to choose from. Okay, so if we go down our list in order, we might start by asking, would the divergence test maybe work for us? That's the easiest one to use when it works. Okay, well, I claim that this is going to be inconclusive. Okay, I'm going to just make that statement without even doing any calculations. Do you see why that might be? Okay, if you look at 2n squared minus 1 over 3n cubed plus 2, you see how the n cubed in the bottom, that's a bigger power of n than in the top. So what that tells us is that if we take the limit as n goes to infinity of this, we're just going to get 0 anyway. So there's kind of no point in doing the calculation if we notice that. We know we're going to get 0, and that's not going to help us. Okay, so we could move on down our list of tests and ask, might the ratio test work for us? Okay, well, remember again, the two things, we need one of two things for the ratio test to work. Either a factorial. Do you see any factorials in our expression? Doesn't look like it. Or constants raised to the nth power, and we don't have any of those either. Okay, so the ratio test, no sense in trying that because it's going to fail anyway. No factorials or constants raised to the nth power. Okay, so we're going to have to try something else. And so really kind of the only test that we've talked about so far that really works well for this is the limit comparison test. Let's give that a try. Okay, so if we start with the term in the series that we're given, 3n cubed plus 2, that's our bn. We're looking for dominant powers, so the dominant power in the top is the n squared, and in the bottom is the n cubed. Again, those are just the things that are growing the fastest in the top and the bottom. Do a little algebra, and that simplifies down to 1 over n. And notice that the series 1 over n is a p-series. Okay, because n is equal to 1, n to the first, this is divergent. Okay, we know that a p-series is going to diverge as long as that power is less than or equal to 1. Okay, and then to actually do the limit comparison test, we need to take this limit as n goes to infinity of bn over an. Okay, remember what those were again. So bn was just our name for the nth term in the series, and an is the nicer series that we're converging to, or comparing to, sorry. All right, so we need to take the limit as n goes to infinity of bn divided by an, which means we're going to multiply by the reciprocal of an. Flipping over an is going to turn it into n over 1. Okay, and this is the limit that we need to calculate. So let's see, we need to do a little algebra here. We're going to take the n in the top and multiply it through the 2n squared minus 1. Okay, so we'll get 2n cubed minus n. And in the bottom, 3n cubed plus 2 times 1 is just 3n cubed plus 2. Okay, and we've got a choice. Do we want to use L'Hopital's rule here, or do we want to use the dominant power method? Okay, really, I think either way would work in this case. So why don't we fall back on L'Hopital's rule this time? I think that's not going to be too bad. Okay, so we'll take the derivative of the top and the bottom. That's going to give us a 6n squared minus 1 over 9n squared. The plus 2 goes away. We can't cancel anything yet. But if we do L'Hopital's rule one more time, we're going to get a derivative of 12n on the top and 18n on the bottom. And now the n's cancel. We get 12 over 18, which is just going to be 2/3, it looks like. Okay, and that result is the number that we call C when we're using the limit comparison test. Okay, so we are ready to write our proof. Okay, and it's going to sound the way that limit comparison proofs always sound. So we'll start by noting that we calculated a value of C, and it was positive and finite. Okay, the other thing that was important is that the series we converged to was divergent. Okay, as a result of the fact that that series that we compared to diverges, our given series also has to diverge. Okay, by the limit comparison test. That's the test that we used. Okay, and there is our answer.